Good morning to everyone present online here. I am Ariyumani Ravanan, Assistant Professor from KIT-Kalaignarkarunanidhi Institute of Technology, Coimbatore. Under the scheme of KIT Knowledge Series, this is our fifth session on FE simulation of laser welding processes. On behalf of KIT-Kalaignarkarunanidhi Institute of Technology and Department of Mechanical Engineering, I welcome everyone who attends this webinar. It's immense pleasure for us to introduce the first person of this session, Dr.N.Sivashanmugam, Associate Professor, National Institute of Technology, that is NIT Trichy. Biomechanics, machine design, risk assessments, tribology, industrial safety, finite element method, welding in friction, TIG, resistant welding, and laser welding are his favorable research areas, and at present, who is effectively working on such fields. At present, as an associate professor of NIT Trichy, who has been supervising so many research scholars and postgraduates in the field of thermal power engineering and industrial safety engineering. Dr. Sivashanmugam has successfully completed more than 5 consultancy research projects, majorly to Bharat Heavy Electricals Trichy and Neyveli Lignite Corporation. Furthermore, he is acting as guest editor for international journals and reviewed for more than 7 journals and publications. Dr. Sivashanmugam has delivered n number of guest lectures across India. Well, in this nice knowledge sharing environment, on behalf of KIT-Kalaignarkarunanidhi Institute of Technology and the participants of this session, we welcome you, sir. Once again, I welcome all the attendees who have shown the interest to take part in this session. Now, over Dr.
Thank you, Ariyumani. Before entering to my today's presentation, I would like to place my sincere gratitude, thankfulness to the doctors, nurses, sanitary workers, policemen, etc., who are working hard towards that coronavirus. And I also thank the chairman of Kalaignarkarunanidhi Institute of Technology for providing me an opportunity to share my research experience to this forum through the webinar series. I also thank my friend Dr. Maniraj, the head mechanical engineering department of Kalaignarkarunanidhi Institute of Technology, Coimbatore, for assigning me a duty to handle this webinar for enriching the research focus to the various engineers who are listening to my speech. Thank you, Maniraj, and thank you, Ariyumani, for giving a nice intro about my career that I have gained at NIT Trichy. Thank you. So now I'll get into my presentation. So my today's topic is on finite element simulation of laser welding process. Before entering into my today's presentation, I thank my gurus, Dr. K. Sankaranarayana, Professor, now Director of NIT Puducherry, and Dr. G. Bonashekaran, Additional General Manager, retired from Welding Research Institute, DHL Trichy. Without their support, this presentation is highly difficult for me to present through this webinar. So my today's topic is on finite element simulation of laser welding process. You know, the finite element is a numerical tool or a numerical technique where you can apply this numerical technique to any field. It is not only the welding part. You can use this finite element tool to any manufacturing process or any physical problem. So the idea behind that, so if you want to understand, if you want to do number of trials in such a way that the experimental methods are very costly, so in order to reduce the experimental experimental work, and you want to get more insight about the problem, the only way or only thing is to simulate the problem and understand the phenomenon. So understand the phenomenon means you have to know something about the problem by searching something in books or in the open sources. Once you understand the problem, once you understand the behavior of the system, you can use any numerical techniques like finite element method or finite difference method or finite volume method, boundary element method. So you can adapt these numerical techniques and you can simulate the problem. Why, sir? What is the need of simulation, sir? When you want to launch a vehicle, for example, if you are working something on aerospace, if you want to launch a vehicle, if you want to launch a rocket, so doing all the experimental part, all the fabrications, and you do the launch, if something is happened to the system, so the entire mission is collapsed. To avoid that, they are going for n number of trials, like they do their simulation using CFD packages or finite element packages, and they find out whether the developed model is going or is working in the correct conditions or right conditions. Once you understand the thing, then you can go for an experimental methodology. Sir, I couldn't get the point. What do you mean about that? Sir, you have to understand the experimental part. So, but there is no need of doing the experimental, but you know something about the experimental work. Sir, after understanding the experimental work, after understanding the phenomena, you know something about what are all the parameters which are directly related to the output. So, sir, if I am changing some input parameter, there is a drastic change in the output. How you are understanding this one? So, there is a correlation between the input and output. So, it is a direct correlation or indirect correlation. So, these are all the parameters which are directly attacking the output. So, how you are understanding the parameters? By doing the experimental part. Now, my question is, if you want to change each and every parameter and you are doing the experimental work, so automatically you are spending the money, you are debuting the person, and you are unnecessarily wasting the time. In order to reduce the time, money, and men, so what you have to do, you understand the phenomena. Once you understand the phenomena through literature or through the previous experimental work, or get the knowledge from the expertise. Once you understand the phenomena, use the appropriate tool. Either you can use the CFD packages or a finite element packages, and you tune your input parameter, and you can develop the simulation, and can develop the finite element model or a CFD model. Then run the model n number of times by changing the input process parameter. Once you change the input process parameter and you are getting an output, I am not giving a very good idea that the output what you are getting by changing the input is 100% correct. It is because you are using only the approximation tool. The output what you are getting is also an approximation solution, approximating solution. So, but you can get more insight about, sir, there is a direct correlation between the input parameter 1 to the output. Sir, there is only a minimal relation, minimal effect between the parameter 2 to the output. So, then you can suppress the parameter 2 and you can give more concentration to the parameter 1 without spending the money, because you are playing with the computers, you are playing with the packages. So it is only of initial investment. There is no need of investing each and every time, because you are going to use only your knowledge for fine tuning the parameter. For this, with this preamble, I am getting into the presentation. So my today's job is I am correlating, I am using the finite element package ANSYS and COMSOL for simulating the laser welding process. You know, laser is light amplification by stimulated emission of radiation. So, and also as per that Newton's law, the energy neither be created nor be destroyed. I am using the light energy light energy is converted to heat energy, which is used for melting the material. Upon solidifications, you are getting out the joint. So the thing is, I want to, because laser welding is somewhat quite expensive. Doing all these things with the experimental methodology by changing the input parameter is very, very difficult. So in order to simulate the process, I am using the ANSYS as a main finite element tool or a finite element code to understand the correlation between the input parameter and the output parameter. Don't worry, my dear friends. So I will tell what are the input parameters associated with the laser welding and what is the objective function, what is main objective to get the adequate well-being geometry. I'll get into this. Sir, already I told you, so this finite element is a general tool. Whatever may be the field problem, you can use this tool. For example, my problem, my manufacturing method or my problem is associated with structural, thermal and also fluid flow. So three field problems are available in my objective function. So my problem is associated with structural, thermal and fluid flow. So taking three field problems at the initial stage itself, it's very difficult, my dear friends. So what you have to do, that's why we are doing lot of assumptions in such a way that make the problem a cumbersome problem. I am making the problem as minimum as possible. I am checking only one small portion of that problem and I am going to simulate. For example, if it is of welding, so it involves thermal, structural and also fluid flow, because once you are heating the metal, it is changed from solid to liquid, liquid to vapor. Upon solidification, liquid is once again transformed to a solid. So now three fields are associated with this welding problem, but taking the three fields for initial itself, it's very difficult to simulate the actual condition. What I am going to do, first I am going to do only the thermal analysis. Second part, I am going for a structural analysis. Why is a structural? Because whenever you are heating the material, automatically thermal stresses are induced inside the body. Whatever may be the heat energy that you are going to use, it may be arc or maybe a light or maybe electron beam or maybe a friction, whatever may be the heat source, the main condition, the main phenomenon behind that, you want to melt the material. So for example, when you go for a solid state welding, you can ask me, sir, when I go for a solid state welding, you are not melting the material. No, you are not melting the material, but you are going to attack at the molecular level. You are crossing the AC3 temperature, upper crystallization temperature. You are going very close to the melting point. So once you are melting the material, automatically thermal stresses upon solidification, stresses are induced in the body. So these two fields are inevitable when you are considering a welding problem. What is the two field? First one, you have to do the thermal analysis. Second one, you are going for a structural analysis in order to find out the distortion of the material. You know, when you see in the roadside a person who is having that electrode in the hand, a torch in the hand, he is doing some stick welding on the material. See, he is putting a lot of clamps on the material and he is not allowing the material to freely expand. So he is constraining the material because you need some joint. What is that? So for different joint configurations, he is putting a lot of clamps, and the clamps are used in such a way that to avoid the distortion. But during the welding, if you remove the clamp, you can see the material is totally distorted. You see, when you during welding, if the person who is doing the welding is unknowingly remove the clamps from the basic material, automatically the material will be totally distorted. So to avoid that, you have to put a proper clamping conditions. Why you have to put the proper clamping conditions? In order to reduce the distortion. Okay, so in order to reduce the distortion, okay, so you have to heat the material. Upon solidifications, you have to put the clamp during the welding to reduce the stress, to reduce the distortion, because residual stresses are induced inside the body. Relieving the residual stresses is very difficult. That's why you are doing the structural analysis after completion of a thermal problem, thermal analysis. You have to find out the thermal stresses. It may be of tensile or it may be of compressive in nature. Clear? So when you are doing a structural problem, for example, I am doing only a civil engineering problem, there is no other involvement of thermal. So we have to do only the structural analysis. For example, if you are taking a cantilever beam, you can fix the one end and you are applying a load or maybe a UDL or uniformly distributed load or uniformly varying load or a point load. whatever may be the conditions, you can do only the structural part. So before taking the problem, you know something about the basic phenomena behind the problem. For example, welding, it consists of 3 different fields: fluid flow, thermal, structural. But doing the 3 field at a time, it's very, very difficult. I am going to suppress the fluid flow problem by assuming a proper assumptions, and I am going to suppress the fluid flow problem. I will concentrate only on structural analysis and thermal analysis. First, I will do the thermal analysis. I am taking the output of the thermal analysis. I am feeding into the structural part to find out the distortion of the material. Because the thing is, you have to adapt the proper methodology to find out the solution of the problem. What is the methodology you have to follow? For that, you have to do the literature survey. Very, very important. You have to do the literature survey. That's why before doing any simulation, you have to understand the physics of the problem, phenomenon of the problem. For that, you have to do the preliminary experimental trials. So you can see whatever may be the papers you are reading out, a literature, it may be a journal articles or it may be a open sources. You have to understand each and every word given in the literatures. They can clearly explain about. Before doing any simulation, you understand the physics of the problem by doing preliminary experimental trials, or get the information from the expertise, or you can get the information from the open sources. Okay. When you go for this structural analysis, my dear friends, in every slides, my intention is to not only giving an exposure. Please listen my lecture carefully. Each slide is having its own meaning, so you can do your research in different part. For example, I am taking only a structural problem. There is no need of thermal. So I will concentrate only on the structural analysis. When you go for a structural analysis, is used to determine the displacements, stresses, strains, and forces associated in the structures or a component caused by different loads. These loads are listed below. The kinds of loading that can be applied in a structural analysis include an externally applied forces, or it may be a pressure load. Only the thing is the unit is different. When you go for a force, it is something in Newton. When you go for the pressure, it is something about Newton per mm square. Or when you go for this industrial analogy, industrial terminology, it is something about kgf per mm square, or they are normally given in terms of megapascal, kilopascal. So steady state inertial forces, when you are throwing a ball from the top, you have to incorporate the gravity, because it is falling towards the gravity, not away from the gravity. It is moving along the gravity. So in that case, you have to give the gravity as the boundary condition, as a loading condition, and imposed non-zero displacement. For example, if you take a simply supported beam, one end is fixed, another end is something about it slides. So then you have to give a proper displacement to simulate the real problem in a finite element code. Either it may be ANSYS or Abacus or COMSOL or Nastron, Patron, NASA, whatever may be the packages that you are going to use it, you have to give the proper boundary conditions in such a way that you have to simulate the real world problem, or you have to simulate the problem that you have taken out for the analysis. Sir, I want to impose the temperature. Sir, it is not in room temperature, it is something in an elevated condition. Then instead of 30 degrees centigrade, instead of 35 degrees centigrade, you have to impose the temperature prevailing in the condition. For example, I am working in the cryogenic condition, so then it is something about minus 250 degrees centigrade or minus 50 degrees centigrade, that is related to the structural part. So these are all the 4 different loads. These are all the 4 different loads where most of the structural analyzer are utilizing for that problem. Okay, so now we are going to the next part. So the thermal analysis, because it depends upon the problem that you are going to do the simulation. Sir, FEA, when you go for the thermal analysis, the finite element analysis is capable of both steady state and transient analysis. It may be a time dependent problem, or it may be independent of time. transient analysis of any solid with thermal boundary conditions, because I am going to heat the body, and there is a boundary conditions where the heat is propagating inside the material by means of conduction. There is a heat transfer, convective heat transfer, or it may be leads to a radiation effect. These are all you have to incorporate into your model, both in steady state or in the thermal, according to the problem that you are selected for your research. That's why I repeat once again, before doing the simulation, my dear friends, please understand the physics of the problem. Steady state thermal analysis, calculate the effect of steady thermal loads on a system or a component. So you can take it as an entire system, or you take only a part in the system and do the analysis. Such loads include the following. It may be a convective heat transfer, a convection, radiation, or it may be a heat flow, or it may be a heat flux. You know, heat flux is something about heat flow per unit area. It is something about joules, or it may be in terms of watt per mm square or watt per meter square. Heat flux, it is pertaining only to the surface area. When you are talking something about the volume, it is called heat generation. So there is a vast difference between heat flux and the heat generation when you are going for doing as a giving as an input, that is a loading condition to your problem. That's why you have to understand the problem carefully. Okay, heat flux is something about joules per watt per mm square or watt per mm square. When you go for heat generation rate, it is pertaining to the volume, watt per mm cube or watt per meter cube, joules per mm cube or joules per meter cube. Or you can give a constant temperature boundary conditions, that what we discussed in the structural analysis. You are doing something on trial conditions or something on elevated temperature or subsurface temperature, whatever may be the thing, you have to impose the loading condition with respect to the constant boundary condition, constant temperature as a boundary. Okay, so you know, because so far what I discussed with respect to the finite element analysis, now I am getting into the application part. So I am focusing only a small applications like pertaining to the automobile industries, but laser welding using for all the industries. It is working in working in shipbuilding industries, aerospace, that is aviation industries, food processing industries, petrochemical. But when you go for a real applications, it is predominantly utilized in automobile industries. That is the photograph I have showcased here. This I acknowledged Welding Research Institute. Without their help, I am getting a raw information from Welding Research Institute from my guide, Dr. G. Bhuvaneshekaran. Here the thing is, I am acknowledged here for getting the photograph from him. So this is one of the typical applications you see. This is the shielding gas arrangement, and this is the laser. So you know, laser is invisible to eye. It is only the light energy. When you are impinging the laser on the material, the light energy, the energy that is the heat that is generated is visible to eye. The laser is not, is invisible to eye. It is for that, for the application pertaining to this welding of door frames is something about product that is a big giant automobile sector, Chrysler. Okay, this is the photograph. And so with this photograph, these are real applications. Now, during my preamble, I have discussed what is the purpose of doing the simulations? You want to get the effect correlation or the correlations between the input as well as the output. See, when you go for the laser, I already gave the expansions of laser, light amplification by stimulated of emission. It is high energy photons. This high energy photons is used for heating the material upon it cross, when you are heating the material, when it is crossed the melting point, you are allowing the material to, so you are removing the heat energy, you are removing the laser. Upon solidifications, you are getting the proper fusion of the joint. That is called fusion welding process. Clear? So the laser welding is a keyhole welding. Now I am going to give some information pertaining to laser beam welding. The laser welding is a keyhole welding process having a concentrated heat input. I will give more information why it is called concentrated heat input. To obtain the required weld bead profile, the quality of the weld, the correct process parameters have to be selected. It's a very, very important sentence, my dear friends. I have tested this sentence please, my dear friends, you can also taste, because whenever you are tasting something, then only you get the full flavor of the food. So that's why I'm emphasizing here. So whenever you are reading something, you with your full Joe's mode, you read something to the literature and get full information from the literature. See, when you are getting a very proper weld bead joint or the quality of the welder, you have to tune the input process parameters. What are the input process parameters related to the laser beam welding? It is of beam power. So normally when you go for a conventional arc welding, we are talking something about current, voltage, welding speed. But here the terminology is totally different. The nomenclature of laser beam welding is different. We are playing with the high energy photons. It is not a welding current or welding voltage. It is called beam power. It is given in terms of watts. There are beam power. It may be a 500 watt laser or 200 watt laser or 1 watt laser. When you are going for a marking, see, when you go for a jewelry shop, a Lalita or Joe's Algas, whatever may be the thing, they have encrypted something, a BIS symbol in the rings or in the ornaments that you are going to procure from the jewelry shop. So these and all, it's marked with the help of low power laser. It is in terms of milliwatt, 500 milliwatt laser. The laser pointer what you are using is also same thing, but it is operated with the very minimum beam power. See, if you are operating with a very high beam power, you are not supposed to use the laser beam. Otherwise, the normal laser pointer what you are using in the classroom, if you are operating with a very high power, then if you focused anything on the wall or something, that will be a burn. The paper will burn because of a high power, high beam power. So these lasers are very operated with very minimum power to do something, a marking. So after completion of these things, you can go to laser engraving, laser melting, laser surfacing, laser cladding. So many things that you can use with the help of a laser. And with the advent of science and technology, there are so many new lasers are coming, fiber lasers are coming, where you can operate with a very small box. You can carry the laser and you can focus the laser any point that you want to do the welding or marking or cladding or a surface treatment, anything. So when you go for this laser beam welding, so the input process parameters are beam power, welding speed, beam angle. Because you are playing with the light, you can focus, you can tilt the laser into any angle. It may be, if you want 65.2 degree, you can tilt the angle. That is why the beauty of laser is playing a predominant role in most of the automobile sectors, or if you do some intricate welding. Sir, the access point is very difficult, sir. You have to do some small welding, a small spot welding using the welding. I want to weld a very small portion. Then the only solution for that problem, you have to operate with the laser. That is nothing is that. We have only one solution if you want to do some welding on intricate areas with the help of a laser, not with any other technique. No other technique in this world to access to do the welding in a very small area. Either you can go with the plasma, but plasma, that is a little bit problem. But if you have a laser, then you can easily focus the laser to a very narrow point and you can do the welding. That is why in most of the jewelry shops they are using the laser, because you are not getting the burn through. Because if you put more power with the other welding technologies, then jewels are very costly. You have see the golds are very costly. If something is happened, burn through occurred, then it is unnecessarily melting the jewel, melting the gold. You are end up with a very huge loss of the material. That's why they are operating a very minimum power laser energy for doing some engraving on the ornaments with the help of these lasers. Okay, so beam power, welding speed, beam angle, spot diameter. Don't worry, I have each and every parameter. I have a slide. I will explain in and around about the parameter. Don't worry. And the exposure time. How much time you want to expose the laser? Sir, instead of 1 minute, if you operate it for 1.5, then it will burn through, it will end, the material will get into that, and automatically the material will be vaporized to the atmosphere. It is of mere wasting the material. Instead of fusing the material, you are vaporizing the material. The condition in welding, you have to melt the material. You are not supposed to vaporize the material. If you vaporize the material will go out, and you are not getting the proper fusion, and you are using the loosen. You are supposed to you are end up with the material loss, huge material loss. So this is a schematic representation of laser beam welding. I am giving a definition about the keyhole, because the keyhole technology, there is only 3 welding processes are available in the world. That is called the keyhole technique. First one is of laser, second one is of electron beam, third one is of plasma. These 3 welding processes are coming under the category of keyhole welding. What do you mean by the keyhole? Sir, please, I repeat, please listen, my dear friends. Sir, as soon as the laser impinging on the material under the beam partly vaporized, leaving behind a hole called keyhole. I repeat, as soon as you are impinging the substrate, laser beam or impinging on a substrate material, substrate means it may be a gold, or it may be a steel, or it may be a glass, whatever it may be the thing. As soon as you are impinging a laser beam on the material under the beam partly vaporized. Because of the high intensity power source, the material will partly vaporize, leaving behind a hole. So you see, there is a hole is created below the laser, below the incoming laser beam. So this hole is called the keyhole. Why, sir, keyhole is specialty in laser, electron beam and plasma? Because you are operating the power intensity distribution, something in terms of 10 power 5 watt per centimeter square. 10 power 5 watt per centimeter. So it is a very high heat in a very high energy density. If you are focusing a very high energy density to a very small point, it will directly pierce the material, and it, after piercing, you see, the material which is encircled the laser beam will be partly vaporized because of absorbing the very high heat from the laser, and because of this absorption, it is automatically converted from solid to liquid, liquid to the vapor, and this vaporized material will create a plasma plum. So this vaporized material will create a plasma plum which encircles the laser beam. So whenever the laser beam is coming out from the laser head, once it is impinging on the material, the vaporized material will encircles the plasma. This vaporized material will come out from the keyhole which encircles the laser beam, called plasma. So what happened? This plasma will absorb the most of the energy from the incoming laser beam. It will not allow the laser beam to digging the material. Instead of that, the energy will be wasted, will be absorbed by the plasma. To remove the plasma, we are using that shielding gas arrangement that I have showcased in the previous slide. You see, copper tube is inserted here, which is kept very near to the incoming laser beam. Why, sir? The 2 important duty of this shielding arrangement is to answer, which is used to remove the plasma and also to protect the build puddle from the atmospheric contamination. So, 2 duty of the shielding arrangement is to, first one, you have to remove the plasma. What is the plasma? The vaporized material which are ejected from the substrate material, to remove the plasma. Second one, which protects the molten build pool, because molten pool or a build pool, because molten pool means it is in the liquid stage, it is having an affinity to mixed with the atmosphere. When it is mixed with the atmosphere, automatically oxide formations are there. You are having some inclusions, entrapment of oxygen leads to porosity. So to avoid the welding defects and also to remove the plasma, we are using the shielding arrangement. Shielding gases are, with a variety of shielding gases we are using in welding processes, especially for laser welding. We are going to use that. We are utilizing a helium or argon, or the combination of helium plus argon. It is called inert gas. It is of 100% purity. So industrial pure argon or industrial pure helium. So helium gas are quite expensive. So for most of our welding trials, we have utilized argon because argon is less expensive compared to the helium. 50% helium or 50% argon. So combination of gases also can be utilized to optimize the output parameters. What is the output parameter? Once after completing the welding, if you cut the welding, do the metallography examination like polishing and etching, you can see the weld bead geometry. Weld bead geometry that is the output parameter, that is the desirable quality which will judge the quality of the weld. So that's why I have used that word to obtain the required weld profile. Weld profile means weld bead geometry. So it is like that. I'll just draw that weld bead geometry. So a small example. I am using a pen here. So for example, this is of plate. It is of square butt joint. This is the joint. So if you want to see what is the weld geometry, so this is that weld. Okay. So sectioned view. So I have used that hatch lines. So this is that bead width, and this one is of DOP, that is of depth of penetration. DOP. This one is something about the bead width. So the main utilization of this finite element package is to predict the weld bead geometry for different input process parameter for finding out the weld bead geometry. Weld bead geometry means it is of bead width and depth of penetration. See, laser itself is quite expensive. If you use that expensive tool and if you do n number of trials, it is also quite expensive. You have put a skilled personnel to do all the experimental trials. So it is a wastage of money, men, as well as the material. Men, money, material, as well as another thing is of a time. So to avoid that, once you understand the phenomenon behind the laser beam welding, I can take a finite element tool, finite element code, either ANSYS, Abacus, COMSOL, whatever may be the thing, and I am converting the tool to my physical problem. What is a physical problem here? So light energy is converted to heat energy. So first we have to do the thermal analysis. For this presentation, I am going to focus only the thermal part. I am not getting into the fluid flow as well as the structural part because the time allocated to me is of 1 hour. With this 1 hour, I want to cover in-depth pertaining to the simulation part of the laser beam welding process. So now you have clear-cut idea. So I just to recollect what I discussed here. So I have given out the numerical tool. What is the use of numerical tool? You have to simulate your condition, simulate your problem. So your problem may be addition of thermal analysis, structural analysis, and fluid flow. First, if you are in the initial stage, don't take all the problem in take a 3 different analysis. First, you cut short 2 analysis and concentrate only on 1 analysis. Get the more information. Then subsequently go for the coupled field analysis. What do you mean by coupled field analysis? First, you are doing the thermal, then go for the structural. You are adding these two to find out the temperature distribution and also stresses. That is called coupled field analysis. Structural plus thermal. Or first doing the structural part, then do the thermal, or do the thermal part, then do the structural. So these and all you have to understand by taking out the open sources or the literature or preliminary experimental trials or get the opinion from the expertise. So now then I focused to one figure where the laser is used for building a rim of a car. It is in the Chrysler company. So they are using the shielding arrangement for removing the plasma and also protecting the weld pool. That is the molten pool or the weld pool. And after that, I define what do you mean by the laser beam welding. So laser beam welding is coming under the category of keyhole welding. Other keyhole welding processes are plasma and electron beam. So these 3 processes are coming under the category of keyhole. What do you mean by the keyhole? As soon as the laser impinges on the substrate material, the material under the beam partly vaporized, leaving behind a hole called keyhole. This vaporized material will encircle the incoming laser beam, that is called plasma. The duty of the shielding gas is to remove the plasma from the incoming laser beam to utilize the full energy which is coming out from the laser kit. So the plasma, you have to suppress the plasma. And what about the input parameters? We have beam power, welding speed, beam angle, spot diameter, exposure, and the output geometry and output parameters of that the output geometry is that bead width as well as the depth of penetration. So the main thing, you have to correlate the input process parameter with the output. You have to fine tune all the 5 or 6 input parameters to get the desired weld quality. So these are all the things I have discussed for the last 15 to 20 minutes. Okay, now another thing, because each and every slide will give a different research area, my dear friends. Please be focused on my presentation. So what do you mean by the Tailor welded blank? So this is a very, very popular in nowadays in all manufacturing sectors. Why it is called Tailor welded blank? So what is the duty of Tailor? So he is going to join 2 different color cloths with the help of that sewing machine. See, it is of tailor made. What is your need? What is your need? You can do it. Sir, I want to join inconel with the stainless steel. Do it. That is a possibility. That is called Tailor welded blanks. According to our use, you are joining 2 dissimilar materials. That is also called Tailor welded blank. 2 dissimilar thickness. Sir, if you take a car, if you take the monocoque of the entire car, so it is not having a uniform thickness. See, I am joining a 3 mm thick sheet with a 1.5 mm thick sheet. So it is called tailored made. So it is called tailored made. According to our intention, according to the requirement, I am going to join 2 different thicknesses or 2 different materials. That is why it is clearly given here 2 or more pieces of flat rolled steel with the similar or dissimilar gauges. Gauges means it is of thickness, or it may be a coated, or it may be a uncoated one, or with 2 different property material. So when you are joining these 2 different materials, it is called Tailor welded blank. Sir, my intention is to join 1.6 mm and 0.8 mm. Sir, for example, if you take a dental clip, sir, so I think if you have anybody is having the experience of going to the dental doctor, they'll put a dental clips. Each one is of different foils. It is of different thickness. What they'll do, they'll put a wire. Wire is welded with the foils of 0.5 mm or 0.6 mm. So then we have to control the heat input. So the only technology what we have is of that laser. With the help of a laser, you can put a very, very small spot. That spot is sufficient to fuse a wire on the foils. That is not possible in the arc welding process. So when you go for tailored made type of welding, so the only technologies are available, but it is of expensive. Though we have to rely some numerical simulation tool that whether my proper set, that the parameter set that I have made, that I have incorporated in the simulation will give a better weld bead geometry. Sir, my beam power is of 50 watts. My welding speed is of 50 mm per minute. That is sufficient to fuse the wire and foil. Then you have to do the simulation and find the proper fusion. Sir, I am getting a proper fusion, sir. Then you go for the experimental. Otherwise, if you take a titanium, if you take another platinum wire itself somewhat expensive. Titanium itself somewhat expensive. And if you do it experimentally, you are not getting a proper fusion, then you are wasting the money, material, as well as the time, labor, etc. To avoid that, when you go for this tailored made type of welding, do the simulation first, then go with the experimental part. So that I have given here, you can go for the high strength alloy with the low strength alloy. You can go for a weight reductions. Why, sir, you can go for a weight reduction? Because most of the aerospace industries now, they are migrating to the titanium as well as the composite material. Why, sir? Because they want to reduce the weight of the vehicle, weight of the launch vehicle, to get the desired efficiency. See, nowadays you see in the motor car, every car is replaced with from aluminum to the composite structures. Why, sir? Because you have to reduce the weight to get the fuel efficiency. So you have to go with a very high speed with a 250 kilometer per hour, 100 kilometer per hour. Why? How they are getting a very high speed? By reducing that weight. So they are playing with the challenging materials. If you are playing with the challenging material, it is very, very costly to get the challenging materials. And getting the challenging materials and doing an unnecessary experiment, trial and error experiment to lose the material. Instead of that, you can do the simulation, get the insight, then go for the experimental work. Okay, sir. So these are some of the typical applications of tailor welded blanks. You see, without tailor welded blanks, it's very difficult to create a monocoque. This is called a monocoque of a car. So all these things are made up of with a different thickness material, different materials. So when you assemble all these things, you will get a beautiful car structure. So everything it is listed over here. What are the areas where they are going for tailor welded blanks? Okay, so these are all something out of day-to-day applications. They are mostly used the tailor welded, that is of laser hybrid welding. So now so far what I used is of the tailor welded blanks. Now I am going to introduce the hybrid process. So you know something hybrid. What do you mean by hybrid? Two. So you are adding two technologies under one tree to get the advantages of two processes. What do you mean by the laser hybrid? Sir, I am going to connect GMAW process with laser. Sir, what do you mean by GMAW? Sir, everyone as a mechanical engineer or maybe the engineer, first semester, you have undergone a subject called basic mechanical engineering. In that, you know something about gas metal arc welding. It is also called MIG. It is of metal inert gas welding. So they are using a consumable filler wire to deposit the filler wire on the substrate material, on the joint what you are in need. Sir, what is the advantage of GMAW? What is the advantage of the laser? Why you are adding the laser with the hybrid? Don't worry. So these are all the different applications of the laser on real and cars. We have a wheel housing Ford Mondeo, as well as floor panel of Mercedes C, B pillar of Fiat Punto, front door inner panel of BMW 5. So many things are there. Without laser, it is inevitable to develop a monocoque structure of any car frames. Okay. So this is the typical picture which will give an insight, which will give an information related to laser hybrid welding. See, before getting into the schematic, I want to share a very, very important information pertaining to laser. What do you mean with that? The parameters related to the laser. Sir, beam power is the energy and the welding speed, we will be aware of that because how far in what speed you are moving the welding head. That is of the laser head. That is related to the welding speed. Sir, you are talking something about the spot diameter. Sir, give some information about the spot diameter because we are playing with the light energy. So when you are putting a laser pointer, so doing the classroom lecture, we are using, when you go for a PowerPoint presentations, you are using a laser pointer. Here itself I'll show. So there is a laser pointer here. So if you take a laser pointer, so this red color which is available in my presentation, it is of laser pointer. You see the size of the pointer is something around 2 mm. I think so. 2 mm or 3 things. I think everyone can understand. So I am moving the laser pointer in the presentation in my PPT. So the approximate diameter of the red color, what you are seeing in the presentation is something about 3 mm or it may be a 4 mm. See, you are focusing the beam power, the entire beam energy to a 3 mm spot diameter. So how you are getting a 3 mm spot diameter? Because you are undergone a 11th standard and 12th standard experiments by using the concave and convex lenses. Light source is available. You are focusing the inverted mins are available. You are focusing a small pin or the tip of the pin on the right hand side of the wall. Like that, you have made some experiments. See, what is it? You are focusing the entire energy to a very small diameter by changing the focal length of the lens. What do you mean by the focal length? The distance between the wall to the lens, correct? So when you are adjusting the focal length, automatically you are enhancing the image of the picture or image of the person or image of the pen, whatever may be the image that you are focusing. When you are adjusting the focal length, you are changing the size of the image, correct, my dear friends? Same thing we are utilizing here. See, the focal length as a thumb rule, when you are using a NdOG laser, niobium, yttrium, aluminium, alumina garnet, that is of NdOG, yttrium, alumina garnet, neodymium. So it is of solid state laser, and if you are using a proper optics, so I will give a thumb rule. If you are using a 200 mm focal length, because the focal length is equal to 200 mm, the spot diameter what you are achieving on the substrate material, on the mirror or on the wall is of 1 mm. Sir, 200 mm focal length, it gives that 1 mm spot diameter. There is an equations are available, but as a thumb rule, because I am not getting more in depth to the equation part because it is time consuming, as a thumb rule, what we gained during our research period, I am sharing to you. As a thumb rule, if you are using a 200 mm focal length, you are getting out a spot diameter of 1 mm. And if you are using a 180 mm focal length, you are getting a spot diameter of 0.9, 160, 0.8, 140, 0.7. If you are using a 100 mm focal length, you are getting a 0.5 mm diameter. Sir, why it is called keyhole? See, my dear friends, if I am operating power is something around 500 watts or 1000 watts beam power, you are focusing the 1000 watts to a very small diameter of 1 mm. If you put so 1 mm beam diameter means what is that? You have to put pi by 4 d square. Pi by 4 into 1 square. So then 3.14 divided by 4, you are getting something around 0.8 or 0.9. So 1000 watts divided by 0.9 or 0.8, you see the energy density is very, very high. It is something around 10 power 3 watt per centimeter square or watt per mm square, because we are playing with the mm. So it is of something around 10 power 3 watt per centimeter square or mm square. See, very high energy is focused on a very small spot diameter. That's why you are getting a very high deposition, very high intensity beam is piercing the material. So what is that? So that's why you have to properly use the beam power. If you use the 1000, it will penetrate. If you are using it the foils now, it will burn through the entire material. You are getting a hole. Instead of fusion, you will get a hole with the diameter of 1 mm. So then you have to use a proper beam power. So beam power something around maybe of 50 watts or 25 watts. You have to concentrate on 1 mm diameter to join the foils. Sir, if I am operating with the 500 watts, then you are getting a hole. Instead of getting the fusion, you are getting a hole. Sir, what is that? When you are going to compare the energy what you are acquiring from the laser with the conventional arc. Oh, very good question. I want to answer that question. How we are going to compare with the conventional arc welding? What do you mean by conventional? This MIG that I showcased here, MIG welding. What is it? MIG welding is a metal inert gas welding. What do you mean by metal inert gas? You are using a consumable filler wire. See, the consumable filler wire. What is the diameter of the filler wire? Sir, my filler wire diameter is of 1.6 mm. So how we are getting out the arc? When you are touching the filler wire, see, otherwise you leave the MIG, you go with the stick welding, normal. In roadside, you can see a torch with the electrode. The electrode diameter is something around 10 mm. For example, you take the diameter of the electrode. In the roadside welding, they are going for doing some joints. When you want to create this one grills, if you go to the grill shop, if you go to the welder, they will take stick welding in their hand. They are doing that welding for making out the grills, door panels, etc., etc., sheds. If you want to do the sheds, the welder will come with will carry this handheld electrode machine, that is a stick welding machine in the hand for doing the that is stick welding to create that panels, etc., and all those things. See, the electrode they have placed is something around of 10 mm, and the arc what you are getting, what you are established is something at a diameter of 10 mm. So the power and to current. So when you go for finding out the power, it is something about current into the voltage. If you are operating with a 60 amperes, and the voltage is something around 10. So 60 into 10 is something about 600. That is the power. In the laser, we are using the beam power. In the commercial arc welding, we are calculating the voltage into current. Voltage is equal to 10 volts, and amperage is something about 60 amperage. 60 into 10, totally 600. You are concentrating the 600 kilowatt to a 10 mm diameter. See, we are playing something in laser for 1 mm or 0.1 mm, but here the energy is focused on 10 mm diameter. So where you are getting a very high intensity, in laser you are concentrating the power on 1 mm, but in commercial arc welding process they are concentrating for 10 mm. So it is 10 times greater. So the energy is concentrated on 10 mm diameter, but in laser it is concentrated on 1 mm. So that's why when you operate with the laser, you can penetrate in more. You can penetrate in depth, but the energy is dissipated is very high in the commercial arc welding process. That's why you are not getting a high penetration, high depth of penetration, and instead of high depth of penetrations, you are getting a shallow penetration, but the bead width is very high. That is clearly given here, my dear friends. That is the full information pertaining to the spot diameter and the beam power. See, my dear friends, you see the laser, this is the bead width. So this is that, I'll use that pen now. So this is that bead width. So this is the bead width, and this is the depth of penetration. You see, depth of penetration, bead width is very, very small, but here you can go with the MIG, you have wider bead width, and the penetration is also, when you compare it, it is very small. So bead depth of penetration is small, but when you are taking the advantage of MIG with the laser, you can get a quite good bead width, and you can achieve the depth of penetration. Why, sir? You want to get the bead width as well as that depth of penetration. You see, there is a problem. It is like a small cup. You can see from this figure. You can see a small cup, because this leads to this leads to imperfection. It is called undercut. It is called shallow. So it is like a cup formation. When you apply a load, so the arrow, in this fashion, if you apply a load on the material, the crack will be propagated like this. The crack will be propagated here. So to avoid that, you need some reinforcement height. When you get the reinforcement height, if you add a filler wire, you can get the reinforcement height what you have shown in this picture. So when you use the MIG in combination with the laser, you can get a reinforcement, and also you can achieve a good depth of penetration. That is the beauty behind the laser hybrid welding. You see, normally when you operate only with the laser, the watts is something around 2 kilowatt. But here it is not 2 kilowatt. Within 1.5 kilowatt, you can achieve the penetration as well as a quite bead width. Sir, why you are in need of bead width? Very good question, my dear friends. So what is that? So if you go for joining a square butt, see, I am drawing a square butt because this is a sheet number 1. It is a cross section. I am drawing the cross section. This is sheet number 1, and this is another sheet. Please don't mistake me because I'm using the cursor for drawing the picture. I'm not getting a proper drawing because I'm drawing with the help of a mouse. I am not using any pen. So this is a sheet number 1 and this is sheet number 2. If I am maintaining a gap between the two sheets, if I'm using a laser here, so laser is coming here and it is used to, this heat energy is used to fuse the material. But what I have insisted you, what I have discussed with you, if you are using a spot diameter of 1 mm, see, if the gap between the two sheet metal is of 1 mm and the spot diameter what I am used is of 1 mm, the entire energy will go into the 1 mm gap. Instead of fusion, the entire beam energy will be wasted between the gaps. Clear? I repeat, my dear friends, the spot diameter beam what I used for doing the joining is of 1 mm. But I am not properly maintained. I have maintained a air gap of 1 mm between the two sheet metal. If 1 mm gap is maintained, if my spot diameter is of 1 mm, the 1 mm, the energy which is concentrated on 1 mm diameter will get into the gap. Instead of fusion, this entire energy is wasted in between the gap, which is maintained between the two sheet metal. To avoid that, sir, I am not supposed to maintain, because a airtight main drawback of laser beam welding, tightness between the two sheet metal. The tightness should be maintained in terms of 40 microns. If it is more than 40 microns, your laser will not penetrate the material. Instead of that, the entire energy will be wasted in between the caps. So the airtight preparation is required to do the welding. I'll show when I show the photographs of the joint what we have made at Welding Research Institute. I'll show if the gap, if there is a gap, then don't use the laser. Then use the commercial arc welding process to join the material. But foils are not possible. Only the sheet metals are possible to join with the help of commercial arc welding process. Sir, what is that? What is it? Then tell me a technique. If I maintain a gap of around 1 mm, you use this laser hybrid technique, because you are getting the advantages of deep penetration from the laser and bead, very high bead width from the MIG. So even though you are maintaining a 1 mm gap, you are using a MIG as a hybrid, because both are joined together. Laser plus MIG torch are combined together. You can see it is a typical picture. I want to acknowledge the Fronius here. They have maintained the technology here. So this is laser is coming here. So this is upside down. Clear? It is down. It is kept on the floor. This is the MIG torch and this is the laser head. So laser is coming. So when you are putting a plate over here, so laser is coming from here and wire is feeding from the MIG torch. So these two are deposited on the substrate material. See, you are getting a penetration as well as the bead width like this. So this is the weld bead geometry. So the terminology associated with this technique is called gap bridgeability. I repeat, it is called gap bridgeability. Even though you are maintaining a gap between the two sheet metal, with the help of laser hybrid, I can take the advantage of MIG. If I take the advantage of MIG, I can get the bead width. If I take the advantage of laser, I can getting a more depth of penetration. With more depth, with more bead width, I can bridge the gap. That is why it is called gap bridgeability. Okay, so this is the beauty thing. You see, with the laser, even though the gap is of very high, it is something around 1 mm gap. So with the help of a laser hybrid technique, so the parameter also is indicated here. Welding speed maintained something around 2.4 meters per minute. For 60 seconds, it moved at around 2400 mm. So, and with the same welding speed, only with the laser, you are not getting the gap bridgeability. You see, there is a lack of fusion, and it is that called, and this imperfection is called undercut. So undercut leads to, when you are applying a load over here, you are getting the fracture at this location. Undercut leads to the weld imperfection. Clear? So with these two things, I think so. I have enriched your knowledge in laser hybrid as well as the laser beam welding process. So this is another typical example. Whatever may be the joint configuration, you see it is like a fillet. It is like a L joint, that is of like a T joint. It is like a lap fillet. Whatever may be the joint configuration. I repeat, joint configurations like a lap seam, lap fillet, T-joint, square butt joint. The things I have drawn in the presentation is of square butt joint. We can do lap seam, lap fillet, T-joint, and whatever may be the position, you can keep that. You can orient the laser head and do the joint configurations. You can do the overhead positions or 2G position or 1G position. Whatever may be the positions, you can tune the laser according to your vision. And this is something about a welding speed of around 8.1. It is a very high speed, my dear friends. It is something around 8,000 mm per minute. With 60 seconds, you can move with a very high speed of 8,000 mm. Okay, sir, why to do modeling? Sir, so far I have discussed with you what is the purpose of modeling. Modeling is the art of abstracting or representing a phenomena. That's why first itself I asked you, understand the phenomena before doing the modeling. Geometric modeling and simulation via computers. Once again, I'll change it to laser pointer. So on simulation via computers, I have reached a level to replace the real-time prototypes or the trial runs. See, you can minimize the trial runs and you can simulate the system with the help of a computers. A geometric model is defined as the complete representation of an object that includes both its graphical and non-graphical information. So you can plot something or you can unplot something and do the simulation. So only thing is you have to model the phenomena. For that you have to understand the phenomena, then do the geometry model, then simulate using the computers. Okay, sir, then only modeling is sufficient. Sir, how to cross-check, how to verify the model is correct or not? Then you have to do the actual experimental trials. My dear friends, in this juncture, I want to insist a very, very important thing. When you are writing a research article, when you are doing the simulation, please don't report only the simulation part. You have to validate your results. Validation means you can validate the simulation results in 3 forms. First one, you can validate the results analytically. Analytically means what is that? If you have a governing differential equations, you can apply the boundary conditions and find out the unknown parameter. What is unknown parameter here in case of welding? It is of bead width and depth of penetration. From the heat profile, from the temperature distribution profile, you can predict the approximate bead width and depth of penetration using analytical solutions. See, analytically you can play with the equation. Second, sir, I am not getting any analytical equation. Then do the experimental experiment, do the actual experiment, do the laser welding, cut the specimen, metallographically prepare the specimen, etch it, polish it, and reveal the macro structure to get the bead width as well as the depth of penetration. Or the third one, sir, analytically not possible, sir, experimentally not possible, sir. Then you have other technique, other method is to compare with the previous published research article. Don't take a normal paper, take that SCA indexed or Web of Science, then compare your results with the previous published article. It is very, very important, friends. Without validation, your paper will not be accepted. And with this technology, the validation, the percentage of error should be less than that of 5%. If you are reporting, I am getting a more than 10%, your paper will not be published. So make that assumptions, you reduce the assumption as much as possible, then do the simulation, compare the simulation with the actual experiment. So that's why I'm emphasizing here. Compared with the experimental methods, the computer simulation based on various numerical methods is becoming more and more popular in the investigation of process because of the reduced cost, increased speed of computation, and capability for analyzing the effects of different factors involved in the process separately. You can take a small problem, do the analysis, get the information, compare with the actual experiment, find out the percentage of error, then minimize the assumptions. Sir, first I have assumed 10 assumptions, then I have reduced to 8, then I have reduced to 6, then I have reduced to 4. What is the comparison between the simulation results and the experimental findings? That is the thing, advantage of comparing the modeled results with the actual experiment. Okay, sir, this is a right moment, it is a correct moment to define what you mean by the finite element analysis. So it is not there in any books. Please understand, it is a very pakka definition of a finite element analysis. A FIM is a mathematical technique. You can add a computer-aided mathematical technique because you are playing with the high computing things. So you can add, a FIM is a computer-aided mathematical technique for obtaining approximate numerical solution, my dear friends. It will give only an insight. It will not give the actual solution, but it will give very close to the actual solution, to the abstract differential equation. 1 minute, my dear friends. Approximate numerical solution to the abstract differential equation that predicts the response of the physical systems subjected to external influences or boundary conditions. That is why during the initial stage itself, I have given out what is a loading condition and what is a boundary condition. So with the help of a finite element technique, you can get the approximate numerical solution. What is that? It will give that entire correlations with the physical phenomena. What is the physical problem you have judged, you have thought in your mind that you are doing in the finite element packages. It is a physical representation of a problem. See, and you are applying the boundary conditions and loading conditions to the problem, and you are finding out the solution for the problem. Why I am using that word computer aided? Because you are playing with the matrices. I think if somebody attended my finite element lecture, you can understand what do you mean by the matrix manipulations. If not so, so I can request KIT to arrange a separate session on finite element, and I can play something with the matrices. So a powerful program that helps in manipulating matrices for solving simultaneous equation is used for this purpose. So it is background behind the finite element method. You are going to play only with the matrix. With the matrix, you are finding out the unknown parameter. What is unknown parameter here in welding? We are finding out the bead width and depth of penetration. See, when you're going for a step, sir, whatever may be the packages, this is the step you are going to follow. Whatever may be the package, ANSYS, COMSOL, Abacus, Nastran, Patron, NASA, whatever may be the package, this is the thing. So the first 5 steps is called pre-processing. The first 5 steps is called pre-processing. 6th step is called solution phase, and 7th step is called post-processing. First 5 steps is called pre-processing. If we go to the ANSYS window, you can see in the left-hand side, we can pre-processing, solution, and post-processing. First 5 steps are of pre-processing, and the 6th step is the solution phase. 7th step is the post-processing. What is the pre-processing? You are assigning the element, what type of element you have to select to do the analysis, and how you are applying the material properties, everything in the pre-processor. Applying the loading conditions, boundary conditions, everything is related to the pre-processor. What do you mean by the solution phase? You are going to solve current load step. That is coming under the solution phase. What is the 7th step? You are reviewing the results. Sir, I want to find out the temperature distribution. I want to find out the von Mises stress distribution. I want to find out the principal stresses. I want to find out the displacement, the deformation, etc. That is coming under the post-processing. This is something about the general steps followed in finite element method. Okay, sir, why FIM for this welding problem? So this is a slide which gives basic information why we are applying finite element method or a numerical simulation tool to simulate the laser welding process or a welding process. See, heat developed during welding process, heat, because the light energy which is coming out from the laser head will be impinging on the substrate. That the energy is converted, light energy is converted into a heat energy. The heat developed during welding process intermittently interact with the workpiece over a very short time interval. So you can see 8,000 mm per minute. See, if the length of the weld, if you want to do a welding of around 1 meter, see the welding speed what you are followed is something around 8 meters per minute. So it is something around within a fraction of seconds you are crossing the 1 meter length. So in each and every time intervals, you see one end part is heating, behind the part is something about cooling, heating, cooling, heating, cooling. So if you want to really simulate the conditions, if you want to understand the basic physics behind the welding, then simulation is very, very important to understand what is the temperature is prevailing before the heat source and behind the heat source, before the heat and behind the heat. I will show when I am showcasing the results. The weld bead is the product of number of overlapping spots welds, and every point in the weld area experience a complex series of thermal cycles during the passage of the welding heat source. So it is self-explanatory. So every point you have heating as well as cooling, heating as well as cooling. So if you want to understand what is really happening in that area, so then finite element method via simulation is very, very important. This complexity implies that analytical modeling techniques are almost impossible. See, because of very fluctuations and all those things, writing equations by using the variables, by using the differential equation or integral equations is very, very difficult. So only thing is you can go for actual experiment or doing the simulation. Actual experiment is costlier, then you have to go only with the simulation technique to understand the behavior. The finite element modeling, therefore, is the preferred option, although the analysis requires a very large number of small time steps. That's why when you go for analysis, you are writing all the load steps. Each load step is having a substeps. Each substep is having a further substeps. So then if you load like this, then each substep. So if it is in minute, if seconds, minute is a load step, seconds are the substep. In substeps, you can go for a microseconds. So in each second, in each increment of time, you can find out what is an enhancement in the temperature or what is a decrement in the temperature. I will show. Don't worry, my dear friends. I will show the simulation, then you can test it. Okay. So going to the experimental part, I want to thank, in this juncture, I want to thank the Welding Research Institute for providing me the experimental facility to conduct so many experimental trials at the laser welding facility. See, this is the power source available at Welding Research Institute. It is a 2 kilowatt ND laser, solid state laser, neodymium yttrium aluminum carbonate laser welding system. Each compartment is, so the 4 compartments are there. Each compartment is capable of producing 500 watts, and this is the laser head. And already I have discussed with you, you can tilt the laser head to attain a different beam inclination. So that is another thing, another very important information is available behind that I will tell. So this is the entire computer numerical control, because it is a radiation. It will create a harmful effects to your eye. That's why the entire system is closed. It is invisible. You can see only the heat, only the that is a back reflection you can see in the monitor. That is at only the what you can only the fusion area. That is at only that fire, that small fire you can see in the monitor, and this is the cross wire. So this cross wire is used for aligning the laser on the substrate. Sir, for example, I want to do a circular weld, then this cross wire will be properly aligned on the circular section. So this cross wire will lead that the laser is following the correct path, like what you are maintaining in the gun. So if you put a gun, if you want to shoot something, there is a cross wire, same thing. Same method also we are following here, and you see there is a shielding arrangement, cross jet of gas. This cross jet of air is used for cleaning the incoming laser, because it is only a light energy where you have a dust particles. You are using a air curtain to remove the dust particles from the incoming light energy. Incoming light is nothing but a high energy photons. And you see that is a fixture. This fixture is used for holding, for clamping the base material, the substrate, to avoid the distortion. And this beam, this laser heat is entirely tilted. Why is that? Because we are playing with the light energy. That is one interesting information I'll share when I'm showcasing one schematic representation. So this is the arrangement available at Welding Research Institute for doing the experimental trials. And this is a beauty thing. So when you are playing with the light energy, so you have to ensure that all the energy is distributed in the circle, in the spot diameter. Correct, sir? So already I have discussed with you, whatever may be the beam power that you have set in the system, that should be properly focused. That should be properly focused in the spot diameter. You see, there is a small graph. What it indicates now, it is like a Gaussian profile. What it means now, the entire energy is distributed inside the spot diameter like a Gaussian distribution. It is called TEM00 mode, transverse electromagnetic mode. It is nothing but intensity distribution measured over beam across cross section. I repeat, TEM00 mode. What do you mean by TEM00 now? The entire energy is focused inside the spot diameter. What do you mean by the transverse electromagnetic mode? It is judged, it is measured in such a way that how the heat intensity distributed over beam across the cross section, over beam cross section. When the beam is coming out from the laser beam, when you cut the beam, you can see how the heat is distributed. That will give an idea behind that. TEM00. Sir, we have any other TEM? Yes, so many TEMs mode are available. TEM01 is there, TEM10 is there. Please note down, my dear friends, after completion of the class, you can get more information about transverse electromagnetic mode, TEM00, TEM01, TEM01, TEM10 are all used for laser cutting. The same thing, if you change the laser head cutting nozzle, instead of welding nozzle, if you put a cutting nozzle, you can use the same laser for cutting the material. Instead of fusing, if you are cutting the material, there we are using a different transverse mode. TEM00, TEM01, TEM10, TEM11, so many modes are there. So this is the instrument which was procured under our DST project. This is used for tuning the laser in such a way that the heat is distributed, whether the heat is distributed properly inside the spot diameter. That is given clearly in this picture. This instrument is called BA500 Industrial Laser Beam Analyzer. This is a glass. So you can ask me, so if you put a light energy on the glass now, the gas will break. No, it will not break. It is the GG arsenic made glass, GG17 glass. This gas is having the capacity of absorbing the laser beam. Once it is absorbed, you can see the cross section of how the heat intensity is distributed. Okay, sir, this is the way the heat is distributed. So now the laser is ready for doing the trials. This is before doing the welding. You have to tune the laser in such a way that whether we are obtaining TEM00 mode to ensure that we are doing the experiment. You are doing that beam density information. Okay, so the experimentation, I have used that very popular steel. So many research articles are coming out for this material. It is called EN8 material or 18-8, 18% chromium and 8% nickel. It is of SS304 stainless steel. The melting temperature is something around 1400 to 1455. So it is having a wider applications. It is used in petrochemical, it is used in automobile. Most of the automobile components are made with the help of SS304. It is called austenitic stainless steel. We have a ferritic, we have martensitic. This is of austenitic stainless steel and it is of 18% chromium and 8% nickel. Carbon is very, very minimum. You see, carbon is less than of 0.05%. It is something around less than 0.1%. Okay, so when you go for a laser beam welding simulation, so you can understand now from nowadays, I think so far you have understand the thing of laser beam welding, laser hybrid welding, why finite element method, what are the input parameters, what is the output, what is the desirability level, everything we have checked, we have discussed so far. And when you go for doing the simulation, it is a computer program. I am using ANSYS parametric design language, APDL. Please make a note of it. APDL, ANSYS parametric design language, is utilized for simulating the entire process of the welding. Okay, wow. Sir, I have used the laser beam analyzer to find out the beam spot diameter. Not only the beam spot diameter, ensure that whether it is operated in a TEM00 mode. Beam incident angle, I want to explain what you mean by the beam incident angle. Don't worry, in the forthcoming slide I will explore. Beam exposure time, how far you have to open it. Sir, it is exposed for 1 second or 1.5 second or 3 seconds. Everything we will discuss in the forthcoming slide. And laser power, what is the power I have operated? It is a 600 watt or 500 watt. Depends upon the thickness of the material to be welded. You have to select the laser power or the beam power. You can use the terminology beam power or laser power or welding power, whatever may be the laser welding power. That is also in normal use. See the keyhole radius, because keyhole, it is a vaporized state. It is very difficult to capture the keyhole by using the analytical formula. So that's why I given an input from the literature. I am using the analytical formula to find out what is the approximate keyhole radius for the corresponding beam power. There is a correlation between the beam power with the keyhole radius and also the exposure time. Sir, it is not, I have not measured anything about the keyhole radius. I have derived it from the literature. With the help of the formula, I can calculate what is the keyhole radius for the given beam power and the exposure time. So now my simulation starts. What is how to do the simulation? Sir, I want to teach the answers that I am doing the simulation of laser welding. So laser welding, how I can teach to the answers? Because the answers is a generalized package. I want to teach it. I want to do the simulation of the process. Then appropriately, I want to select the heat sources. What is the heat source, sir? For a conventional arc welding, we have a different source. For laser, we have a different source. For friction welding, we have a different source. Because you have to take all the heat source. Each source will give information pertaining to the welding process. Sir, when we go for a laser welding, I am using a surface heat source equation and also volumetric heat equations. Why is a surface heat source equations? I want to find out the temperature distribution on the top surface. What do you mean by the volumetric heat source? When the laser is impinged on the substrate, it is digging the material. In what portion, in what shape it is digging the material? Either it is in terms of conical or it is in terms of a shallow. Depends upon the shape of the profile. I want to select the heat source. That's why initial presentation itself, I told you first you understand the phenomenon behind that laser welding. See, if you take the laser welding, it is not like a shallow penetration. It is like a deep penetration. So then I want to correlate the shape of the bead with respect to the heat source distribution that I will show in the next slide. And I am constructing a three-dimensional model using that finite element packages, physical model. Take the physical model, mesh the model, convert the physical model to a finite element model. Apply the temperature dependent material properties because you are doing a material non-linearity. Only three types of non-linearity available in the finite element analysis. First one is a geometrical non-linearity. Second one is a material non-linearity. Third one is the contact non-linearity. Please make a note of it. Geometrical, material, and the third one is of contact type non-linearity. This type of a problem is called, the problem what we are doing is called material non-linearity problem. Why, sir? When you are heating the material, automatically your thermal conductivity will be decreased or increased, depends upon the material. See, when it is in the room temperature, it is having a thermal conductivity. For example, 15 watt per meter square degree centigrade. Yes, it is of watt per meter square degree centigrade. And when you go for the thermal conductivity, see, it is a 15. When you are increasing the temperature to 100 degrees centigrade, it is not 15, it is something about 10. So you have to teach the answers. The material what I have considered is depend on the temperature. When you are heating the material, it should automatically extract the particular thermal conductivity from the lookup table. When you are feeding the material property, a careful examination is required. how you are getting out the material property from the open sources or from the material library. Give the informations. Why? With the room temperature, its behavior is different. When it is in the elevated conditions, the temperature is different. When it is in elevated temperature, the behavior is different. You have to teach the answers that the material behavior is very depends upon the temperature. And you are giving the loading conditions and initial conditions, like what I have discussed in that heat transfer analysis, that is a thermal analysis, and feeding to the informations, and finally you are getting out the temperature distribution. From the temperature distributions, I am predicting the weld bead geometry. How we are getting out the weld bead geometry? See, in the problem, the melting point of stainless steel considered for this present study is of 1400. Once the temperature is crossed 1400, the resulting profile is called weld pool or molten pool, or called weld bead geometry. Please understand, my dear friends, I repeat, once you do the temperature distribution, what are all the temperature crossed beyond the melting profile, the area which is coming under the melting profile is called weld bead geometry, is coming under the purview of weld bead geometry. See, so this is the sequence I have followed. So same thing, it is in the flowchart form, it is in terms of another flowchart form where I use the temperature dependent properties like conductivity, density, enthalpy. Why it is enthalpy? I am considering the phase transformation, because solid is converted to liquid. Upon transformation, upon solidifications, you are getting you are getting out the liquid from solid, from liquid to solid, solid to liquid first. Upon solidifications, you are getting liquid to solid. So initial boundary conditions, applying the heat flux, giving the heat source equations, apply the load step, develop the solve the problem, and find out the temperature distribution. See, it is a normal mathematical description of the problem. It is of heat conduction equations. QU is represented the heat source model. What I consider for this is the power generation per unit area. So the power what I am going to give is given in terms of these equations, and it is getting into the heat energy on the substrate material. Okay, so I have discussed so many things. What are the different heat source models are available? Apart from three things, there is so many heat source models are available. We have modified Gaussians are available. In plasma arc welding, they are using a different sources. So based on the weld bead geometry, based on the physics of the welding, based on the resulting bead wind, the researchers are writing their own volumetric heat source. But for my problem, we have utilized only the three-dimensional conical heat source. How it is that? This is a schematic representation of the conical Gaussian heat source. I'll show in the forthcoming slide. This is the predominant thing. It is called Goldberg heat source model. This is called double ellipsoidal. For conventional arc welding like MIG, TIG, stick welding, they are using this double ellipsoidal heat source for doing the simulation. Sir, what do you mean by the Gaussian that I already discussed with you? I have used the industrial beam analyzer to get the Gaussian distribution. Why, sir? How the heat is distributed on the top surface. So the conical Gaussian is addition of Gaussian at the top and conical at the bottom. See, this is the beautiful representation of a conical Gaussian. The top is of the Gaussian representation. Inside, for example, if you take a sheet metal, the top surface, when the laser is impinging, when the laser touches the surface, the distribution of the heat on the top surface is of Gaussian. When it is penetrating, for example, if you take Z is equal to 0 at the top, Z is equal to -1. -1 means it is getting into the material. When Z is equal to -1, the shape of the heat distribution is like a conical. This is acquired. This is acquired based on the geometry of weld bead. The weld bead, what we are obtaining during our preliminary experimental trials, is like a conical in shape. That's why we are using a three-dimensional conical Gaussian heat source. I repeat once again, this 3D conical Gaussian, it comprises of two parts. See, it is divided into two. First one is the surface, second one is the volume. Surface, you see, it is a surface because it is taking only along the x and y. At Z is equal to 0. This is Z is equal to minus h. So if we take the h is the thickness of the material, h is equal to Z is equal to 0 at the top surface, X is equal to H at the bottom portion of the material. So we have two surfaces when you take a sheet metal, top one as well the bottom surface. Top surface we consider Z is equal to 0 and bottom surface Z is equal to H. H is equal to thickness of the material. So with these equations, I am feeding this equation to my finite element code in order to simulate the volumetric heat source. What do you mean by the volumetric heat source? What is the behavior of the laser welding? How we are getting the behavior of the laser welding? Once I am getting the weld bead geometry, based on the shape of the weld bead geometry, I am selecting the heat source. Sir, if it is for commercial arc welding, it is like a shallow penetration, then 3D conical Gaussian heat source is not required. In that case, you are going for gold duct double ellipsoidal heat source. Sir, when you go for a friction welding, these heat sources are not possible to do the simulation. You can go for a frictional heat. From the frictional heat, you have to do the simulation for doing the analysis on friction welding processes. Clean? So this is something about the surface heat source and something about the volumetric. Each terminologies are given here. I will share this presentation to you. This and all, it's very, very simple. Q at the top and Q at the keyhole. So the keyhole radius I have gathered, I have extracted from the literature. And another very, very important point I want to emphasize here is something about the percentage of absorbability. Sir, even though you are operating a 1000 beam power, so this entire 1000 watts beam power will not get into the material. So it depends upon the affinity of the material. So see, if you take a cooker, when it is a copper bottom, so when you commercially procure a cooker, if it is of copper bottom, it readily accepts the heat. Correct? It is readily accepted the heat from the stove. Clear? Because it is having a very good affinity. So if it is not copper bottom, if copper bottom is not available in the cooker, it takes so much of time to get the heating of the entire thing. See, so based on the material property, the absorbability will be different. Will different. The thing is, the absorbability of the material will depend upon the property of the material. So based on the absorbability, you are absorbing the laser energy. See, that is the thing I have discussed here. Q keyhole, that is of energy which is absorbed in the keyhole, is not the 100%, it is only of 75%. How we are extracting this information? Sir, by doing a number of trials and error method experimentations, we come to that even though you are giving a 1000 kilowatt, 1000 watt power, the material will absorb only 750 instead of 1000. 750 will be extracted will be absorbed by the material. Remaining 250 watts will be removed, will be wasted as a energy, will be wasted. Okay, so only 750 watts will be absorbed by the material. Like that, whenever you are doing the simulation, first understand the process, then find out the efficiency of the process. If you take a MIG welding, the entire energy will not be absorbed by the substrate. Only the partial energy will be wasted. Only the remaining energy, maybe 75 energy is absorbed by the body, 25 or 80. It depends upon the process. It is varied, depends upon the process. Okay. So when you go with the different joint configurations, this is the way I want to fit the heat source. It is like a square butt joint. This is the joint line. This is a weld trajectory. When you cut that, it is this sheet number 1 and sheet number 2. This is only with the sheet number 1, how we are going to simulate the heat source, how we are going to simulate the process. If it is of a G joint, it is like a vertical sheet and horizontal sheet. This is the way I want to tilt the laser beam and I want to impinge in the laser on the weld trajectory. This is the weld trajectory. When you go for a lap joint, it is called lap seam. It is like similar to the butt joint. You are impinging the substrate, you are impinging the laser on the substrate on above the sheet. If we are placing one sheet one over the other, it is called a lap joint. You are impinging the laser on the top surface of the top sheet. Clear as? So now, based on the boundary conditions, what is the boundary conditions? It is a entry. The initial conditions are time t is equal to 0. At time t is equal to 0, temperature should be in the room conditions. T0 is the room temperature. During the entry of the laser, I am entry. See, if you take the axis, this is x-axis. X-axis represents the width of the substrate material. Y-axis represents the length of the substrate material. This is the way I am going to feed the laser. I am going to feed the heat source here. So this is moving along the y-axis at y is equal to 0 during the entry. So during the entry, it is at the initial condition. During the entry, the entire substrate material should be in the room temperature. T0 implies the room temperature. Okay, so what about the natural boundary conditions? Because I am talking about the laser irradiation. So radiation means energy will be dissipated. Laser irradiation means it's absorbed. Laser radiation means energy will be wasted in terms of radiative heat transfer. But laser irradiation means it is absorbed by the substrate material. So according to the natural boundary conditions, I have considered 3 modes of heat transfer: conduction, convection, radiation effect. Okay, so this is the thing. When I discussed with the beam incident angle, this is the point I want to highlight here. You see, if you keep the laser head straight, because we are playing with the optics, my dear friends, we are orienting the laser by changing the optics because it is only a movement of light energy. And by fiber optic cable, you are transporting the laser from one portion to the another point. And with the help of the optics, you are impinging the laser to the spot diameter of the beam. See, if you are putting a straight beam, it is a light energy. So most of the energy will be getting into it, and some partial energy, because it is a light energy, it is reflected by the substrate material. See, so I think there is one small black color arrow is highlighted here. So if you are operating a straight beam, because of the back reflection from the substrate, the back reflection will create damage to the optics. See, when you take the laser head, it is only with the optics, with the lenses. So because of the back reflection, it will damage the optics. To avoid the back reflections, what we are going to do, we are tilting the beam with some angle to avoid the back reflection. If there is a back reflection, the energy will collapse the entire laser head. To avoid the back reflection, to protect the optics, beam optics, to protect the fiber optics and also the lenses, the beam should be tilted in such a way to avoid the back reflection. You see, this is the tilt beam and this is the reflection. It is 80-degree beam and 85-degree beam. This is 80-degree and 75. Sir, it is only a light energy. So when you are putting a straight beam, the resulting profile, what you are obtaining on the substrate material is like a circle. But we are not going to use the straight beam because of back reflection. It is damaging the lens. To avoid that, we are going for incident beam. So when you're going for an incident beam angle, you are not getting a straight, you are not getting a circular profile on the surface. Instead of that, you are getting the elliptical shape. This is the thing you have to understand by doing number of literature and also understand the physics of the problem. See, if it is of wider beam angle, you are not getting a circle. Instead of that, you are getting out the elliptical shape. That is clearly given in this schematic representation. This is the butt joint configuration. This is the laser beam given in an inclined fashion, impinging on the material on that inclined angle. So this is the molten profile. So keyhole is only of circle. It is of vaporized one. So this is of vaporized material. That's why it is indicated in a red color. And this orange color will give the information pertaining to the molten profile. Upon solidifications, you are getting the bead width as well as the depth of penetration. That is the objective of the work. Clear, sir? So, how it is filled, sir? This keyhole is there. It is similar to the example. If I want to give an example which will be matched with the scenario, means you take a butter. If you take a butter and if you put a pencil inside, if you put a pencil inside, and wherever you are inserting the pencil, that portion of the butter is removed. You see, clear? So when you remove the pencil, automatically the butter which is encircled the pencil, will come and deposit inside the hole. It is like a normal grinder. In the normal grinder, you have in a very old grinder. Nowadays, we are having a 3 stones grinder and all those things. In a older grinder, we have a 1 stone grinder. At the center, we have some cup shape. Inside, you are putting out the rice. You are going to grind the rice. So once it is converted to like a powder form or like a paste form, if you remove that stone, inside. So automatically the circumference, the material which is available in the circumference will come and close that hole. Same thing, that is a scenario behind the keyhole technique. As soon as the laser is there, you are getting a keyhole. When you are closing the laser, when you are cut short the laser, the material which is encircled the material, which encircled the keyhole, will push the which push the material like a centrifugal force, and this entire molten metal will be deposited inside the keyhole. So your keyhole will not be visible to your eye. But during the simulations, during the condition of welding, you can see the keyhole by using the high-speed camera. But the cut section is not possible. But when you see it, when you focus it on the top surface, you can see a very small pinhole that I'll show when I'm showing the real picture of the weld. See, this is the finite element model, and as far as the condition is concerned for finite element model, wherever your concentration is very high, wherever you are doing the simulation, wherever you are doing the simulations, you can see the temperature distribution here. Very high temperature gradient is high at the weld trajectory. When you are moving further, you are not getting a very high temperature gradient. So this area we are going for a coarse mesh, and the weld trajectory is meshed with the fine elements. Okay, fine mesh at the weld trajectory, coarse mesh at the area very far from the weld trajectory. Okay, so totally nodes and elements are depicted here in this picture. Okay, so what about the assumptions? Please, my dear friends, without assumption, it is not possible to do the simulation. See, I am doing only the thermal part. I am not going for a fluid flow part, because when you go for a fluid flow part, I have to consider the convectimal flow, Marangoni convection. You please write a term called Marangoni convection. It is called Marangoni effect, sir. It is a beautiful thing. Because of running out of time, I already crossed my given time. So many informations I can give in a Marangoni effect, sir. When you go for doing the simulation in CFD, you have to consider all those effects, but I am doing only the thermal analysis. Thermal analysis, there is no need of considering all the physical phenomena like viscous force, buoyancy force, convective multiflow, Marangoni effects, etc. And by considering this, I already discussed the absorptivity of the material is only of 69.3%. See, as per the proposed by the Z and Carr in the year 1999, the material absorbed by the laser absorbed by the stainless steel is something only of 69.3. So 1000 beam power, if you are operating with a 1000 watt beam power, only 69.3% of 1000 will be getting into the material, not 100%. And the lumped heat transfer coefficient I have considered for doing the analysis. It was proposed by Fervin and Scott. You have to acknowledge, you have to put the references when you are citing something in the research article. Convection and radiation loads are considered. I already discussed, by considering the phase change, I have taken out the enthalpy of the material, and conductivity, specific heat density, and all are temperature dependent properties. So with the thermal with the laser spot diameter, so now there is no movement of the laser. Where laser head is kept stationary. I am going to do only the spot welding. Why I am going for spot welding? First, I want to understand the behavior of the spot welding. Then go with the laser seam welding. Laser seam welding means I am moving the laser torch. Laser torch is given by a welding speed. You start with the welding speed. It will move with the very high speed of 800 mm per minute or 8000. Whatever the capability of the machines, you can move the torch. So what are the parameters? What are the input parameters? So now I can do the optimization to find out for which parameter set I am getting a very high depth of penetrations by doing the combinations and all. You see, with the different spot diameter, you can see the whole. You can see the pinhole at the top surface. This is because of the keyhole. After removal of the heat source, this molten pool will close the entire keyhole, but it will leave the impression at the top surface. That is why it is called keyhole technique. This is exposed with a different exposure, 0.5 seconds, 1 second, 1.5 seconds. These are all made on the SS304 material. The thickness of the material what I selected for the experimentation is of 3.16 mm. So with the different totally 27 trials we have made, so you can understand the phenomenon behind the laser welding. I already told you, if it is a straight beam, you are getting a circle, almost circle, but we are operated around 85-degree beam angle. You are not getting a circle, you are getting only the elliptical profile. You see, for a wider beam angle, you are not getting a circle, it is almost elliptical. So it's fully elliptical. For different, very high exposure time and very high beam power of 1000 watts and beam angle of 75 degree, you are getting a very high elliptical shape on the top surface. Like that, it is on the top surface. You can do the simulation. You can do the simulation for creating a spot. See, first spot is opened at the exposure of 0.5 second, and you are moving the torch to another location for creating another spot. I repeat, one spot is created at an exposure time of 0.5 second. The laser head is moved to another location because you want to continuously create a spot like what is given in the picture. Spot number 1, spot number 2, spot number 3. You can really simulate the situation by using the ANSYS APDL, that is a ANSYS parametric design language. So you can, if you want to get more information, you go to the YouTube, type ANSYS parametric design language welding simulation. You can acquire more information on APDL. See, this is the scenario. One spot is created, laser it is moved to the other locations. Another spot is created. One spot is in solidification state. One spot is cooling down. Another spot is heating up. You see, two scenarios you can see simultaneously. That is possible only with the simulation. It is not possible with the analytical part. You can see this is in the cooling stage. This is in the heating stage. Almost it is end of the cooling stage, and this is in the heating stage. This is spot number 1 and this is spot number 2. So I can do the simulation. You can see at one junction, at one time, one spot is cooling down, another part is heating up. So these and all, this information you can extract in the post processor. You can see the temperature is something around 2559 Kelvin. So minus 173, that will give the approximate temperature distribution, and you cross the melting point of the SS, because melting point is something around 1450, 1400. If you could add 173, it's something around 1573 Kelvin. But the temperature, what I am given, what I have predicted, what I have simulated, it's something around 2000. It crossed the temperature, it crossed the melting temperature. So the above, when it is crossed above the temperature, what are all the areas pertaining, what are the areas encompassed by the melting profile will give the approximate weld bead geometry. This scenario and all you can easily simulate. You can see one is on cooling down, another one is of heating up. So there is a point, there is a time. At that moment, you can see a beautiful scenario between the spot 1 and the spot 2. Clear? See, so these are all the things, the temperature distribution by utilizing a different heat source. And when I used only the Gaussian distribution, you see, my dear friends, when I gave the profile of the Gaussian distribution, it will give only the top surface distribution. It will not penetrate anything. It will not showcase anything with respect to the thickness of the material that is available here. To check the capability of my code, to check the capability of the code that I have written using APDL, to ensure that I have fed both the heat source model to find out the temperature profile. Only with the Gaussian you are getting a temperature distribution on the top surface, but when you are using a Gaussian or the three-dimensional conial Gaussian volumetric heat source, I can get the temperature distribution on the top surface and also in the thickness direction. See, so you can see, yeah, very conical type of thing in the thickness. When you see it in the front view, you can easily understand the thing. So this is that picture. Wait once again, I will change the. See, so when you do the simulations, you can took the animation video and all those things. First spot is created here, and the laser head is moved from another location. It's moved to the another location. Another spot is created. This part is going to cool down, and this part is going to heating up. One spot is in the heating stage. Another part is in the different state in the solidification part. So these are all the things you can do the simulation, and this will give the peak temperature. Peak temperature means at the end you are getting out the peak temperature, because before closing of that, at the end of the closure of the laser, you are achieving a very high peak temperature. After it reaches the peak temperature, the temperature is declined and attains the room temperature when you're going for the cooling stage. This and all you can do it in the post processing. Okay, so this is once again I'm reading the video. So you can extract, because you can couple with the Excel sheet, or you can couple with the MATLAB, and you can plot that how the temperature is distributed for a single spot, because we are doing only the matrix manipulation. So this is a geometry of the sheet. It is something around 50 mm length and 100 mm width. So this and all you can, like a rectangle box, rectangular sheet. So you can feed the information into your MATLAB code, and you can find out what is the peak temperature at every moment. See, so to understand the basic behind that, you see this is the experimental weld profile. So it is like a almost conical in shape. So that's why I have selected a three-dimensional conical. And it is a straight beam. You can see it is of 90-degree straight beam. So during this experimental, I have damaged the lens. The cost of the lens is something around 12,000 rupees. I have spent from my pocket to procure the two lenses. That is why the cost is very remembered to me. So it is like almost a circle. You can see it is almost a circle. It is a 90-degree straight beam. And why? Because whenever you want to see the capability of the system, you have to damage something and you have to enrich your knowledge. Without failure, it is very difficult to get the fruitful results. So we failed, but we have published in a very good journal. That is the thing I have to focus here. So this is the top surface, and this is along the thickness direction. These two things are validated. The simulation was validated with the experimental, and something around the percentage of error is around 1.2 to 1.3%. Clear? And for different exposure time with the different bead geometry, with the different process parameters, I have compared my finite element simulated results with the experimental thing on both the top surface and along the thickness direction. See, these are all different surfaces. You can see the parameter effect. When you go with the wider beam angle, you are getting almost elliptical. This is almost a circle. This and all you can review the results, and you can fine-tune your input process parameter for achieving the desired results. This is along the cross-section, what is the depth of penetrations, what is the bead width, and you can develop a beautiful graph for publishing the results. See, and this is something on, so far what we discussed is on the SS. So we have made something on COMSOL. This is the user manual. This is a tutorial available in COMSOL. I want to acknowledge here with that, with their presence, with the help of them only, I am presenting this thing to this forum, to this webinar. So this is a glass lab. This glass lab is having a tendency of absorbing the laser beam, and this is glass. The laser is used for melting the glass to weld the glass particles, to weld the glass material. See, these are all the equations they have used in that reflection coefficients, because what we have discussed is 69.3. Yeah, this is a reflection coefficient associated with the RC. This is the absorbability of the material, and this sigma x and sigma y are related to the beam width and stigmatism. If there is any change in the optic, that deviation also you can reach it in the equations. That is sigma x and sigma y. So there is some small changes. The beam density is not properly aligned. That correlation, that change in small effect, you can feed it into the equation to find out what is the correct heat input which is giving into the gas lab. Okay, ma? So these are all the model. This is the area where the heat source is going to, where the laser beam is going to impinge in. This is the finite element model. This is the physical representation of the system. After meshing, you are getting out the finite element model, and you can see the temperature distribution. Okay, ma? This is only the glass lab. You are getting only something around 350 Kelvin. Okay, depends upon the material, your temperature gradient will vary, and the peak temperature will also vary. Depends upon the melting point of the material. See, after understanding the basic science behind the spot welding on the glass, now I have used the welding speed. I am adapted the welding speed to move the laser head and to find out what is the temperature distribution when the laser beam is in the moving stage. Okay, wow. So now there is no exposure time, because in the spot we are going for exposure time. In seam welding, instead of beam exposure time, we are using a terminology called beam welding speed, that is WS. Beam angle is of 85, 80, 75. and gas flow rate for removing the plasma plum, and as well as the protection of the weld puddle from the atmospheric contaminations. I am using the gas flow rate of 5 liters per minute. This will be moved with the help of the copper tubes, and the spot diameter what I maintain is something about 0.8. So 0.8 means it is something around 160. It is something around 160 mm focal length. So it is something about a full factorial design, because whenever you are doing experimental sort of things, you have to go for a design of an experimental technique. It is a full factorial design, and these are the trials I have made in the Welding Research Institute. This is the appearance of the bead on the top surface as well as on the root side. And if you want to see one of the trials, you see this is the heat energy. This is not the laser, and this is the copper tube where you are getting out the shielding gas, and there is a air curtain which is used for removing the dust particles from the incoming laser. Okay, so this you can see all the pin points are there, the pin holes are there because of the key hole. This is the starting point, this is the end point. During the ending stage, you are getting out the pin hole because the material will be closed inside the key hole and it is leaving a small hole. Okay, that is the pin hole, and the operated under the mode of TEM 00. When you go for a cutting, you are operated with the TEM 01 and TEM 10. It is called TEM, transverse electromagnetic mode. What do you mean by the transverse electromagnetic mode? It is a intensity distribution measured over beam cross section. If you understand the thing, intensity, that power intensity distribution over a beam cross section. So, and it was verified with the BA500 laser beam analyzer, and this was simulated with a different load step at the initial period, when the laser is at the entry, when the laser at the middle point, when the laser at the entry stage, and when the laser is at the end. What is the temperature distribution on the surface and along the thickness directions? Both you can do it, and this is the video which is giving an information about the movement. See, at each step you can see. So when I put the hold, you can see this red color gives that a very high temperature, because where the heat source is impinging, where the laser is impinging on the material. From that you can easily understand. You see there is only a preheating zone, because it is a concentrated heat source. When you simulate the commercial arc welding process, you are not getting this preheating zone. Preheating zone is very high, but it is a concentrated heat source. The most of the energy is getting into the material instead of getting from the surface. So surface energy is very minimum compared to the energy which is getting into the material. Surface, that is XY energy distribution in the top surface is minimum, compared the energy distribution is very high along the thickness direction. That's why if you compare the preheating zone is very minimum, and the post heating you see a very wide temperature region. It is something around 600 to 1332 Kelvin. So from that you can see the temperature distribution very easily, but when you do the experimental, it is not possible. That's why YFEM, because intermittently interacting with the workpiece, you are getting alternate heating and cooling. That is why the beauty of finite element method plays a predominant role in getting the temperature distribution and all those things. Okay, so with the help of the MATLAB, you can see how the temperature is distributed from coupled with the Excel sheet or with the MATLAB, and each junction, what is the peak temperature, what is the room temperature, everything you can see. And this is something. So far, I have discussed only the linear profile. When you go for the circular profile, so that is why with the cross wire you can fit it the heat source at that point, and from that you can do the simulation. This is taken out from the console. So we have an idea of to work out with this console. The capability of the console is directly you can incorporate your own equation. Sir, based on the behavior of the weld bead geometry, I have wrote my own heat source model, sir. Whether it is possible to incorporate, yes, you can use console. You can incorporate. Tutorials are available in open sources. Put the temperature distribution profile, laser heating. If you put laser heating, you can get the code behind the console. Okay, so this is another different, this is a conical Gaussian that we have used for the simulation. If you change the profile, like Gaussian is changed to conical Gaussian, conical Gaussian is changed to modified conical Gaussian. So if the weld profile is like this, then is it possible to do the simulation? Yes, it is possible. Only you have to change the equations and the boundary conditions. This is for conical Gaussian and this is for the modified conical Gaussian. So many things are that. So I think this is with a quick brush up. So this is the thing we have discussed. So many about the preheating zone and the post-heating zone. See, with a very low very low welding speed. You see, 400 mm per minute is very slow compared with the 1200 mm per minute. You have a very big heating tail. So the preheating zone is very minimum, and you have a very big heating tail. What we have discussed here, the molten pool profile and all. So this is plasma plus plumb. This is something about the liquid part, and this is something about the solid. When you are impinging the laser, after removal, this entire liquid is converted to the solid. Liquid will be filled in the vapor, and the keyhole will be filled with the liquid. Upon solidification, liquid is converted to a solid, and this profile during the moving of the heat source, you can highlight. You can do the simulation. That is the thing I am highlighting here with the different welding speed, how the heating tail is looking when you are visualizing from the top. Okay, so this is for different joint configurations. I already told you, T-joint we have simulated, lap joint we have simulated. So many things are that, lap joint. So this is the TEM00 mode, TEM10, TEM20, so many modes are available. This is for the lap joint, and we have made the simulations, and this is the sheet placed one over the other. So what is the appropriate power required to penetrate the bottom sheet? So you see, the first sheet, top sheet is penetrated and getting into the bottom. You see, when you are operating with this beam power and the welding speed, you are not supposed to penetrate the bottom sheet. So these are all to check, to cross check whether the beam power is adequate to penetrate, to achieve the full penetration. This and all you can achieve. Okay, so with two different welding profile, beam power, what is the temperature distribution? So once you are writing a code, whatever may be the change of parameter, you can change it. It is like feeding your pets. And whenever you want, you can feed it. You can get the output for different process parameter. Only thing is, you have to teach the answers in such a way that this is the problem I am going to anticipate, I am going to simulate to extract the information. That is very, very important. Okay, so this is a comparison between experimental part and simulation part. This is for the T-joint comparison between the experimental part and the simulation part. And you can take only the elliptical profile. You see, I already told you Gaussian, three-dimensional conical Gaussian, how the temperature distribution on the top surface and also the directions. If you want to take only the molten pool once it is crossing more than 1400, you see 1773, yeah, 1773. So it is of 273, yeah, something 1500 plus 273. So you are getting out that, sorry, I mentioned some 173 Kelvin, it is a 273. If you add, this is the molten profile. Above the profile, what are the area below the curve? What is the area which is crossed melting profile? That area only I have captured and I have showcased in this picture. So like that, once you simulated all those things, extraction of information is up to you. What you want, how to showcase your results, you can get the beauty of the informations. So these are all you can do the simulations. Only you can move the molten profile. The two animation that I have showcased is full entire temperature. This is only of molten pool that is crossed beyond the mold profile. That is a melting point. And keyhole, it is something about, if you know the vaporization stage, what about the area when the laser is moving from one end to the another? The area what is obtaining above the vaporization stage, that also you can do the simulation. You see, it is something around 2300. So it is something around 2000. About 2000, what is a profile? That is pertaining to the keyhole. See, like that, you take the different frames of different plots, you can highlight in your screen. And this is one paper I forgot the name of the author. So they have used that laser impinging on the GG17 class. This is and they have used the high-speed camera to capture only the keyhole. So I have used the same thing. I have compared the simulated results with the previous published literature. I have taken out the property of GG17 class, that is arsenic class, which is having an affinity of laser beam, and I have teach the properties to my coder. I have used the same conical Gaussian, and I have simulated the conditions of laser impinging on the GG17 class, and I compared with the previous published article for different welding speed and for the different beam power. Okay. So with these references, it is highly difficult to prepare my presentations. So in this juncture, I thank all the persons, all the researchers published the articles. Without that, it is highly difficult to prepare and give this presentation to through this webinar. And thank you to all. If you want to post some question, please chat with the KIT moderator. Moderator is there. It's my pleasure to answer your question. Thank you. Thank you, friends. Thank you, KIT, for giving me an opportunity. And especially I thank Maniraj and Mr. Ravanan for giving me an opportunity. I think I could enrich your knowledge in this area. Thank you.
Thank you. Thank you, Dr. Sivashanmugam. Thank you for your being here today. We have received n number of positive comments about this session. In a single word about such feedbacks were highly informative. I appreciate the participants that you took the time to be here and listen to this webinar. Indeed, we had an excellent knowledgeable session from the last 120 minutes. So we hope that you have come to know more and value addition about FE simulation of laser welding process. Thanks for listening. And this presentation will be available in public through YouTube channel, namely KIT-CBE. And I request all the participants that it's very important to fill the feedback form, which is available in the link to receive the e-certificates. Once again, I thank the attendees, and I thank the management of KIT-Kalaignarkarunanidhi Institute of Technology, principal, vice principal, and deans of our institution. Also, our sincere gratitude to Head of Mechanical Engineering Department, Dr. J. Maniraj, and KIT Infonest team for their continuous effort and extending support for making this webinar as a successful one. Thank you, everybody.
And I think you can use the presentations only for knowledge sharing. Don't publish anything from that. If you want to publish, please acknowledge in literatures or in your research article. Thank you.